So, good morning, everyone. This is the first invited talk session of APLAS 2024. And I'm very pleased to introduce Sukyoung Ryu, who is one of my first international friends in the research community, since we were both graduate students a long time ago. And I don't want to say how long. And Sukyoung got a PhD degree from KAIST, and she moved to Boston to join the Fortress project at Sun Microsystems. And then she came back to Korea, and she started a project on static analysis for JavaScript, and she's keep working on programming languages, and she's gonna tell us kind of her adventure in about the programming languages in the wild. So please welcome Sukyoung.
Okay, thank you for the introduction. Hi, I'm Sukyoung Ryu from KAIST. It's my great honor to be here to give a keynote talk. And as Achushi said, our team has been working on designing, documenting, and implementing programming languages. We've been working on JavaScript for more than 10 years. And recently, we are done with JavaScript and moving on to different programming languages. And today, I'm going to tell you about our journey throughout that adventure. This talk is not going to be that technical, but it's going to comment on several papers. So if you are interested in the details, I invite you to our papers. And if you read, when you read and try our open source projects, then you are more than welcome to send us questions and comments, and even better collaboration. Okay, so this is my students. Current students and previous students as well. And 4 of them are here over there, and so Yusung, Harin, Kanguk, and Jihee, they are going to have this student research competition this afternoon, so please stay tuned. Okay, so let's start with JavaScript. I think here everyone knows about JavaScript. JavaScript is everywhere, and according to those GitHub ranking of the programming languages, JavaScript has been the #1 programming language forever. And number 4 is TypeScript. It's yet another JavaScript with some types. So in this audience may think about type soundness, but not really. In TypeScript, it's not really types. They try to use some hints from those static analysis, but again, #1 and #4 are JavaScript and JavaScript variant. And JavaScript is, abused in many ways, especially for little kids. Even my daughter, she started using JavaScript when she was really young. And teachers and people usually think JavaScript is very simple, but not really, right? Let's look at this function f, taking one parameter x. The body is very simple. Return statement of x double equals with negation of x. So you would think this is going to return false, right? If the language is sane, then that's going to happen. But with JavaScript, not really. It's true. And it requires lots of implicit conversion. And in the JavaScript language specification, there is one chapter about implicit conversion. And the main philosophy behind it is like, JavaScript is going to be the language for the web, and people are using web applications a lot, like in every day. So there shouldn't be a surprise in crashing, but surprise in the results might be okay. So that's why they have this thick language specification. So programming language researchers often tease about the JavaScript language, saying that the language semantics is so weird that the language specification is really rigorous. So JavaScript language developers and implementers, they need to understand the semantics. When they read, when they analyze JavaScript programs, they need to think about the same semantics. That's why this ECMAScript and this TC39 is the international committee to take care of the language syntax and semantics. And they released this language specification called ECMAScript. And just like other language specifications, it defines the syntax and semantics. The syntax is, this is extended BNF notation. As you are familiar with this kind of production, when it defines the array literal, there are 3 productions, one at a time, right? And for each production, there is a really well-written semantics in English prose. So here, let's look at this 3rd production. It says array literal starts with this open bracket and element list separated by comma, optional aliasing, and then closing bracket. And the semantics is number 1, let array be the result of this. Number 2, let next index be blah. Number 3, call this function. Number 4, if blah, like that. So they are in English phrases, but very precise, we can say, right? So there are several research groups in the world working on JavaScript analysis. So my later friends, yes. So Julian Dobie from IBM, they have been developing Voila. This is initially Java language analysis framework and now JavaScript as well. And Anders Miller from Aarhus University, his group has been developing TICE. And our team has been developing SAFE. So SAFE, TICE, and Voila have been competing for over 10 years. And we met each other almost every conference saying this time we won and this time you won and all those, friendly competition. And as time goes by, we are understanding JavaScript better. In the beginning, we were we are language guys and, we know how to analyze programs. But soon we realized that JavaScript is not really one of those languages. So it's pure static analysis is not enough. So SAFE has some hybrid analysis, including static analysis and dynamic analysis and more. And Anders Miller's group has their own approaches. And voila, IBM gave up. They do not work on JavaScript analysis anymore. They were like, okay, you guys go on, and we are going to move on to something else. So they are now working on analysis of machine learning code, Python code. So that's it. So we started in 2011, I think. So I joined KAIST in 2009, and we've been working on JavaScript. And our first paper about JavaScript analysis is October 2012. And 10 years later, our tool set is now officially integrated into TC39, meaning that the JavaScript language, thank you, and the JavaScript language is open source. Its language specification and its official test suite all are maintained by TC39 using GitHub. So whenever someone is proposing a new language feature to JavaScript, the committee discusses. And there are 4 or 6 layers of approval. And then finally, the spec editor need to confirm that spec phrases and then put that into the spec and test suite as well. And now, whenever there is a pull request, our tool is checking the language specification and test suite as well. So today, I'm going to tell you about how that happened and how we made it. So after that, May this year, we had this JavaScript language design and implementation in tandem article in CACM. So as you know, the CACM article is not that technical or difficult, so you can take a look at that and read our journey. And there is also a short video about it. So Jens Persberg, he was the head of the computer science department at UCLA, and he's been running executive committee of SIG plan community and all that. And one day he asked me hey, how did you convince them? Them meaning JavaScript developers and those TC39 people. Because JavaScript is well known to be competitive in the sense that that's the #1 language. So big IT companies, they'd like to own the language. And they'd like to make their own decisions about the language, new language features and language semantics. And the community is very, yeah, I would say competitive. When they discuss one feature, there's always loud voices. And so people are aware of that. So Jens was like, how did you convince them? Oh yeah, that's all started with this, our problem with handwritten JavaScript static analyzer. Our team has been reading this language specification, understand the semantics, and the developers, including me and my students, we had to implement the semantics written in English phrases in some way. So there were several calculi about JavaScript core semantics. And when people abstract that, as I said, we have SAFE, KAIST from Anders Miller, Wildlife from IBM, Chase AI from UC Santa Barbara. There were more, actually. And now 3 are kind of surviving. So it has been okay. I mean, the spec, it's well written, and once we read and understand the semantics, it's not that difficult to implement the semantics. In my office, I have this book. Every line is underlined with pencil, and several scribbles and about questions and things like that. So it was okay until 2015. So this spec in 2021 is 879 pages. So in order to understand the entire semantics correctly, we need to understand these many pages. It was okay if the spec is stable, but since 2015, the TC39 decided to release the specification every year. So can you believe that? That's enough for people. And my student back then came to me one day, like, you know what? This is not for a human being. And but I have a crazy idea. He's now a faculty at Korea University, Jihyuk. He was a PhD student back then. And he was like, but I have a weird idea. I think it would work, but I'm not sure. So could you give me like 3 months? So that was, I guess, like April or May. And we were like, yeah, let's aim for ICSI in August because that's a crazy idea. I was like, oh, well, that's cool if it works, but I'm not sure whether that's gonna work. But let's try, 3 months, we can have fun. So that was his idea. He was not happy to read these many pages to implement static analyzer for JavaScript every year. And his long vision was to generate an analyzer automatically from the specification. So generating an analyzer, how? So before that, we'd better get the semantics automatically from the specification. So this is our entire journey from the spec to get an analyzer. In between, we have several trials. Not really trials, several tool sets. So let me tackle one at a time. So this is the JISET paper in ASE 20, JavaScript IR-based semantics extraction toolchain. So that's the beginning. As we saw before, this semantics is really well written. And now that we've been reading these sentences for years, we understand that by heart. And the number of phrases or the number of kinds of English phrases is not that big, right? So it's not like natural language, not the entire English. It's just some patterns with English phrases. So we realized that, and there's a PDF version and HTML version, and the HTML version is rich in the sense that it has various hints about whether it's a name or a constant or a function and things like that. So we were like, we can compile this to our intermediate representation. So that was the main idea. So we designed our language with, again, our syntax and semantics. But this is an intermediate language for describing the semantics of JavaScript. So it's not a programming language like programmers use. It's a meta-level language to describe the semantics of a real-world programming language. So are you with me? Maybe the meta-level always, get some difficulty to be delivered, but don't worry. I will tell you more about it later. So by reading this HTML document and compile it to our intermediate representation. So these single lines are now one line in this program written in our language IRES. Intermediate representation for ECMAScript. And now that we have the semantics, we can extract syntax from this BNF notation, from the spec. We can extract semantics from the English phrases. So for the syntax, we could generate a parser using this lookahead parsing, and parsing expression grammar, but it didn't work by itself. We had to add more lookaheads, but the techniques, the details are in the paper. And we also generated these algorithms as functions, and those number of the patterns in English phrases was 118. Only 118 kinds of phrases in more than 800 pages. So, so we tried to compile those language specifications since 2015, and we could compile 96% automatically. So that's a lot, and we can generate something that may not work. So we tried to see whether the extracted semantics is correct by selecting the latest one and filling in those missing 4% manually, and try to run the official test suite. And for the applicable tests, it passed all the tests. Then, frequently asked question is, what about those 4%? Why you couldn't generate them automatically? Because the JavaScript has long history, there are some features that are implemented first and then specified, like regular expressions. If you are familiar with regular expressions, you know what I mean. So that one chapter in the JavaScript language specification is dedicated to regular expression, and actually that explanation was a translation from C++ code, meaning someone who wrote the C++ code for the regular expression for JavaScript wrote the semantics in English, just like in the same way how he implemented it. So it's not easy to generate the semantics out of that, and we didn't want to because no one is going to write that again. So we just skipped that part. So that was our JISET paper. So we call that mechanized specification, and that is going to be the oracle, meaning that it behaves exactly as written in the specification, right? So by definition, that's the semantics. So we can test existing implementations by using this oracle, right? So what we did is that there are various implementations of the JavaScript semantics by almost every big IT company, and they have their own implementations and their own optimizations. And because of their aggressive optimizations, their implementations have several bugs. Not really several, lots of bugs, right? So we picked several engines, but before that, so these engines are implementing this semantics by top-level researchers and developers all over the world, but we were not sure whether they are implemented correctly, and they need to confirm the semantics written in the spec. So what we did is that because we have the semantics, we also have this oracle interpreter, the behavior of the semantics. We can check for a given test code, JavaScript code, whether these implementations give you the same result, right? So if these green thingies, these engines give you the same result, but this Google V8 gives you a different answer, it's highly likely that there is a bug, right? More important thing or more interesting thing is that if the implementations give you the same different answer and your Oracle gives you a different answer, then it can be a bug in the spec. How can that happen? Because the spec is the Oracle, but not really in JavaScript again. In the JavaScript world, people are really aggressive, and JavaScript developers ask for new language features from different programming languages. Hey, you know what? Rust has this cool feature. Let's add it to JavaScript. There's a cool feature in new programming language. Let's add it to JavaScript. And the JavaScript this committee has way of getting approval and all that. It takes time. So the engine developers implement new features, new feature requests before they got to the specification. So implementation first and then semantics. So in many cases, the engines implement new feature and spec is not, and spec is following that and making some mistakes. So those things happen. So this is our second work test, JavaScript engines and specification tester. So we started with generating some JavaScript seed program and add some mutation to make lots of test data to trigger any bugs in the implementations. And for example, we identify some values or some properties that we'd like to check, right? So there are various properties that we'd like to check. One example is going to be, this is a variable x whose value should be 3. And because we know the semantics, we add assertions in there. Like, yeah, the value of this one should be this. Or there are various properties that we are interested in. And this paper added like 7 properties, but you may want to know different properties, then it's up to you. Because we presented a methodology to add a way to check some properties of JavaScript programs, taking advantage of the semantics in the specification. And our tool, everything is open source. So you can take our repository and you can add some checks by yourselves and then get that checking. So only with those 7 property checking, we could only with those 7 property checking, we could find 44 bugs in engines: VA, GraalVM, QuickJS, Modable Access. We picked these 4 engines because there are really many JavaScript engines, but only those 4 were implementing the latest features. So I'm going to get back to that point later. So only those 4 engines were implementing that, and we could find 44 bugs in there. We can also find 27 bugs in the specification. So we did not expect that, but we were really surprised and happy to see that. Oh, now we can debug the language specification in prose. So whenever we find these bugs, we make bugs to the developers. And this is one, we got some feedback. And this is one instance. For a developer of GraalVM, right now we are running test 262. Test 262 is the official TC39 test suite. So they are running them. So they were testing that a lot. And the V8 and Nation unit test suites. So every engine has its own test suite as well. So they make a change. When they have this CI, they run everything. But still, we are finding their bugs. They were like, what are you doing? Okay. And then the third work is motivated by the spec bugs that we found. So whenever we say spec bugs, another frequently asked question is, what do you mean by a spec bug? Because spec is the semantics, the Oracle semantics. So let me show you one specific example. So this is a built-in function, the semantics of method.round in the ECMAScript. It says, oh yeah, method.round is a built-in function which takes a parameter x, and first, because we'd like to treat it as a number, let's call this two-number function on the parameter and get the result. And let's call it n. And this question mark meaning that some value can be converted to a number, but some value cannot, right? So if it cannot be converted to a number, here there's going to be an exception and it's going to go away. If it succeeds to convert that to a number, then let's call it n. And if n is an integral number, return n. Otherwise, if x is less than 0.5, x came in. So this is a bug, right? Yeah. So because the spec is written by a person, yeah, they can make mistakes. So here in JavaScript, x can be anything. It can be string, boolean, number, object, whatever. And when we call this two-number function, then n should be a number. So since then, we need to use n, not x. So here, where if you run this, there's going to be a crash, and this was really happened. And if they were running our tool, they wouldn't have it, right? So this should be n. So we again made this analyzer. This is actually a type checker of English phrases. This one, yeah. So this English phrases compared to some this data structure, and there we can type check it. So very simple. This is a simple abstract interpretation focused on types, and we again just selected 4 outstanding features like reference checking, error checking, assertion checking, and operand checking. Only with those 4 checking, right. And if we just implement those abstract interpretation framework from Patrick Kuzo, it's too imprecise. So we had to, improve the type sensitivity, and we designed condition-based refinement as well. So again, all those technical details are in the paper, and by implementing that, we could find 93 bugs, right? Yeah, 93 bugs in the spec, and so more important thing is that ES12 was the work in progress specification back then. So even before the release, they were working hard on that, and we found 14 bugs from there. So that was very interesting, but remember, our initial goal is to generate an analyzer. So until now, we've been talking about concrete semantics, running an interpreter and running the interpreter to get some errors and using tests. And now, finally, state analysis. So this time, it's yet another meta level. So I often lose audience at this point. So I will try. I will try to be successful this time. So JSaver, this is a derivation of static analysis. What's the main idea? So until now, until then, all those JavaScript analysis and the JavaScript related tools were kind of compiler-based approach. That's what we phrase, meaning that when you have a JavaScript program, all those safe, ties, and voila, as a developer of those analyzer, we read the specification and we manually compile this. We manually wrote a compiler to compile JavaScript programs to some intermediate representation. Safe had Safe's intermediate representation. Ties has Ties intermediate representation in Scala. Voila has intermediate representation in Java, right? That's how we phrase it. It's like developers, analyzer developers develop those compilers from source language JavaScript programs to their own IL programs. Then they can generate static analyzers out of that. And what we are proposing is, because we are extracting a parser and an interpreter from the spec automatically, we should be able to drive the analyzer as well. Because the spec describes the semantics, concrete semantics, and we extracted that, right? Then static analysis is kind of an abstract analysis, abstracting those concrete semantics. And we already have concrete semantics. But the thing is, this time, the concrete semantics is not for the source language JavaScript, but for the meta-level intermediate language called IRES. So here, there's meta-level. So actual target programs that we'd like to analyze and find errors and bugs are JavaScript programs. But in order to understand the semantics of that target programs, we need to describe its semantics in some meta-level notation. That's our meta-level language. And our interpreter is not really a JavaScript interpreter, but the interpreter for this language. In that sense, it's meta-level. So our interpreter takes a spec and JavaScript program and returns a value. And similarly here, now we call that interpreter-based approach. From this ECMAScript, we do, so we do have this JavaScript interpreter, but actually, how can I, let me try one more time. This is the interpreter-based approach, meaning that here we only get JavaScript program, and this ECMAScript code gives us an interpreter. And we only need to write a static analysis for this interpreter, this concrete semantics. Okay, so more precisely, this is what we implement. So here, we have mechanized specification. I didn't show you this part. What is it? It's from ECMAScript, we extract this mechanized specification. That's done by JISET, right? Then here, by having this mechanized specification, the semantics, the concrete semantics is now written in IRES. That's the semantics we had. And we also have this JavaScript parser. So this JSaver takes a JavaScript program and gets the semantics from this automatically generated parser and the interpreter. We only need to write abstract semantics for this IR semantics. Then when we analyze JavaScript program, we can get the analysis result. That's going to be the analysis result from this analyzer for IRES. Okay, so this is always difficult to get delivered. I'm going to come back to here later with different language. Maybe that's a bit easier to understand. Let's see. So by having this, we compare the analysis results with SAFE and TICE. Again, Voila is now not in this competition. So TICE and SAFE, this is automatically generated analyzer. So how you are supposed to read these graphs. These graphs are my favorite. This is TICE and this is SAFE and this is the generated analyzer. Here, the test suites introduced from 2014, 2015, and until now, recently, right? And for those tests till 2015, both TICE and Voila, SAFE are pretty good. Green meaning that we can analyze them with good results, and red meaning that the tools analyze the programs but give you unsound results. White meaning that the tools cannot analyze them. With TICE, only 25.7 is sound, 25.2 is unsound, the remaining cannot be. SAFE is slightly better, but this automatically generated analyzer can safely, soundly analyze everything. So that was a victory, but as you can guess, it's slow because we didn't care about the performance. It's meant to be an oracle. So this was, our progress, and now JavaScript engine developers are, contacting us more often. Like, my team is curious about the methodology you are using to find these issues. How did you find them? And we, reported all those things to the ECMAScript TC39 community as well, and we sent that to spec editors, and they invited us to explain how we did. And this is from one of those editors, Michael Ficara. He was like, you know what, during my time as editor of ECMA 262, one of my primary goals has been to make the specification easier to consume for automated analysis tools such as yours. Because the main job of those three editors were to read those pull requests and find errors and fixing them. And now that the tools are helping them, they're so happy, and they invited us to the entire TC39 group. And yeah, they really liked it. And all those discussion is also open source. You can read them. And so this was what? January 2022. So we gave this presentation, and in 10 months, we could deliver it to the entire system. So after that, since then, our team has been moving away from JavaScript, but Jihyuk is now the professor at Korea University, so his team is taking it over. But in between, we had another paper last year at PLDI about generating even better test data for JavaScript engines. So last week, or the week before that, there was a big specification workshop in London, in UK. And there are many people working on language manipulation. And one of the main topics they discussed was generating test data for language semantics is really difficult. And I heard, because I couldn't attend, Benjamin Pierce had another group and John Hughes had another group discussing how difficult it is. And this is in that line. So we generate test data, and we could find many errors, but we found that something is different in this language semantics compared to programs, right? What are they? Maybe this is specific to JavaScript, but when we have binary operator, there are going to be lots of function calls in between. If you ever read the JavaScript specification, when you have E1 plus E2, in order to get the semantics, you need to call like more than 20 functions, I think. So, and there, some functions are used in many operations, like binary operations, plus, minus, multiplication, and all that. So if we use the usual test coverage for this language semantics, then that's not that effective. To be precise, I mean, more specifically, let's see. When we have addition, then when we use just node coverage or edge coverage for the semantics of the language semantics, when we call E1 plus E2, we are going to cover every line, and we are done. If we call E1 minus E2, that semantics is already covered, right? So that, because that's how the semantics is written high level in the language specification. But in reality, in JavaScript engines, they have lots of functions to do the semantics because of what? JIT compilation and all those optimizations. If we cover just one line in the spec and done with the testing, then we are not covering much. So this one was motivated by that. We introduced feature-sensitive coverage. It's not only just one function at a time, but the entire feature to get there. And by using that again, we found several errors. And remember that when we try to find bugs in many engines, not that many engines are they are covering latest features. Because again, specs are releasing every year. So many developers and many companies use transpilers. So if you've heard of Babel, so Babel is one of the famous transpiler, taking JavaScript code using latest features and compile that down to JavaScript 1.5. So the most long time ever version for that. So Babel does that really well, but you can guess it cannot preserve the semantics. That was our motivation, and again, there were so many errors that we are still finding errors there. So Kang-wook over there is also working with Jihyuk about improving this technique as well. So this is still JavaScript. So what's next? Now that our tools are officially used by the TC39, and now that Jihyuk has his own group, we were like, okay, Jihyuk, you can take it, and I can say bye to JavaScript, and what's next? So we were looking around, and the next target was WebAssembly. So WebAssembly is kind of the next language for web programming. And people behind WebAssembly, they were struggle and they had too many problems with JavaScript because they wanted to make a real assembly language for web programming, and that's WebAssembly. And the spec is really well written because it started with the motivation. This is a part of its stack, again, binary operator. It has this, ECMAScript-like phrases. But in addition to that, it has this operational semantics. Yeah, it's not that Greek letter yet, but every language feature has this English phrase, prose notation semantics, and this operational semantics. And whenever, before that, so when I was attending a conference, I was like, we are looking for another language. And Sam Linley told me, like, how about WebAssembly? You'd better take a look at it. And what is that? And I looked at it, and there was a Darkstream seminar coming up. So I sent an email to Andreas, and like, we are working on this. I have no idea about WebAssembly, but can I join and share our idea? And he was like, bring your student. So this was the very first day in the morning. Andreas showed his vision about WebAssembly. So WASM, in short, WASM 1.0 was released in 2018, and from 2022, what he's planning to release this language every year. Doesn't that sound similar? Right? So I showed this picture in the afternoon, and we had this cool idea for you. If you are going to release the spec every year, you're going to have similar problems. And while listening to my talk, Andreas started writing an intermediate representation for WASM semantics. And on Thursday, we had a meeting all together. Conrad Watt was taking a picture, so he's not here, but we all got all together, and how can you make it? And by having that, there are Philippa Gardner and many people, Sam Linley here, people are working on mechanization as well. If we can mechanize the spec, we've been working on interpreter and state analyzer and test generation, but they are interested in formal proof, and they can generate code and Isabel and Agda, whatever mechanizations. So we are all excited, and in order for a new language feature to be added to the WASM spec, it's even more stricter than JavaScript. For a feature to be standardized in WASM, 4 key artifacts must be presented. 4 key artifacts. Number 1 is formal specification in this semantics. Because Andreas Rosberg is the main person behind WASM among many people, and he believes in operational semantics. He doesn't think he needs this prose notation. And actual WASM developers way more prefer this notation than Greek letters. So there are 2 versions. The second thing is a prose code description of the feature's behavior. And then the person who proposed the new feature need to provide this reference interpreter in OCaml. And then finally, unit tests. So all those 4 things. Formal spec in declarative style in formal calculus, and prose specification in algorithmic style in prose, and reference interpreter in OCaml, and test suite. All those 4 suites need to be provided. So what we suggested is that, all those 4 things are implementing or describing the same thing. We'd better describe the semantics only once, and all the others should be generated from the single source of truth. So that's the main idea. So this like formal LaTeX version, prose notation, interpreter, and test suite, they are all automatically generated. And the details is in our paper, PLDI this year, this is our paper, and those red boxes are my team, my students, yeah. So, and that was, doctor was last year, March last year, and PLDI paper is June. Just before that, there was the committee meeting about WASM, and our proposal to replace that manually written spec with our generated spec is accepted, approved, with the condition that when the tools, with the condition that we are done with that by the end of this year. So this is the second integration of our tooling to a real-world programming language. So then what's next? So now we are tackling each language at a time. So the current language is P4. So if you've heard of it, it's language for network. So self-defined network. So Nate Foster from Cornell University, he has been making the P4 language cleaner by applying programming language ideas to that. So P4 language was mainly designed and developed by C++ developers. So the language, there is a specification, but not really, we may not call it a language specification because the syntax is here and there everywhere, semantics is everywhere. It says it has type inference, but it's not clear when, what type is inferred, and there's coercion, but again, it's a moving target. So, you know, Nate had got some award at Purple this year, and he said that he believes the PL community should be doing more work in language design, especially in emerging areas, and he contacted us to make the P4 language better in a sense that we can generate a document or implementation automatically, again, from the single source of truth. So we are now working on that, and one of my students gave a talk about mechanized language definition for P4 in the P4 workshop. But this is the beginning, and we are still working on that, and we are learning a lot. What's next? So this is my big picture when we propose a pretty big grant to the government. You know these kind of pictures, right? So I envisioned our plan, and it's like from one source, single source of truth, we can generate various tools, and we started with JavaScript. It took more than 10 years for us, and then WASM, it took about 2 years, and now we are working on P4, and we are interested in Rust, and because of our lines of work, some people from Rust also contacted us like, oh, how about Rust? Can you save Rust as well? And we are discussing that. But Rust is huge compared to the other language, and really real programming language, and there are several calculi, but the intersection is not that big, and there's no specification. There are several attempts to make specification, but nothing yet. So we are working on that. So finally, what have we learned from these journey? So lessons learned. The first thing is every language is different. When we like 2 years ago, I thought I understand what we are doing. So we are like, oh yeah, so we wrote this CSM article, and there should be one single source of truth that language should be able to describe the language semantics, and all the other things, including the language spec, should be generated from this single source of truth. And we thought that IRES, that intermediate representation, is general enough, but not really. It's different with WASM. When we first read the spec for WASM, they were like, push this value on the stack, pop the value. What is push and pop in the language specification? Because it's really low level. And there are work that's much easier to get published. And there are work that developers really love, but it's difficult to get published. This is one example. This is interactive debugger because we have those semantics in the specification. When we have a JavaScript code, we can have a debugger for JavaScript, but at the same time, we can show you the actual semantics corresponding to that JavaScript code, right? So when we evaluate this function expression, and we can show you where where it corresponds to. We can even show you the value of these meta-level variables in the spec. And developers really like that, but I'm not sure whether we can publish this. So in the same line, so it takes a lot of commitment. The JISET paper was September 2020. We had several papers, but in between November 21, we had the first meeting with the TC39 editors. And in January 2022, we had a presentation at the entire group, and it took 10 months. When Jiyeok was a postdoc, he was a postdoc, and with one or two more students, and they had to make it better to be officially integrated. You know, their first request was every implementation until then was in Scala, and they were like, can you re-implement that in JavaScript? What? So we were like, no way, JavaScript, no way. How about TypeScript? So we spent 2 weeks to implement some parts in TypeScript. We were like, we are gonna implement that for you. We are gonna implement everything for you, but in Scala. So now that whole thing is in Scala, and that took like 10 months. So, and another thing is what we have to convince the community. I'm telling you only the successful story until now, right? So we had this presentation in January 2022. But the thing is, 5 years ago, other researchers gave a similar presentation at the TC39. Philippa Gardner from Imperial College London and Schmidt. I'm forgetting the name, from India. They gave this presentation. They showed this secure subset of JavaScript and verification and formalization, but the community didn't take it because it was too theoretical and small fraction of the language and all that. So, but I'm really grateful for their efforts. On top of their efforts, and on top of all those, researchers and analyzers in JavaScript, I think we could make this one step. Okay, so this is the last slide. So this is an excerpt from the reviewer of JISET, the very first paper. And the reviewer said, can you possibly go backwards and generate the documentation from your derived model? That way, the documentation can be more precise and the standards committee can use your model to design new versions of the language. I believe that this the right order to design and document languages, first the semantics, then the implementation and documentation, ideally generated from the semantics. So this reviewer foresaw the vision and the journey that we are doing, and it's easier to be said, but difficult to make that happen. And again, we are currently working on finishing up and wrapping up with WASM, and actively working on P4, and trying to work on Rust. And Yusong over there, he's interested in that, and we are trying to work on that as well. So with this, this is our journey with designing various programming languages, and thanks for listening.
Thank you for the very interesting talk. So if there are any questions. Yes. Oh, wait a minute, there is a microphone coming.
All right, so thank you for the very interesting talk. So I didn't quite catch your sentiment at the end on this slide. Do you think this proposed way is the better way, like deriving the documentation from the model, or the other way around? Because you've been doing it the other way.
I was not precise enough. Thank you for the great question, catching that. So again, in the beginning, 2020, I thought that this is the way to go, and there should be one DSL, and we can describe the semantics of programming language in this DSL, and all the other artifacts are going to be automatically generated. Yeah, the life is beautiful. But the thing is, some languages use big step semantics. Some languages use small step semantics. And actually, JISET had even bigger dream to make bidirectional. Like we have this, DSL, domain-specific language for language semantics, and we can generate document in Korean, in Japanese, right? And from the specification, we can even generate, that's what we did, right? So we can have bidirectional and all that. But the thing is, it's really language specific. So JISET is not that interested in multiple programming languages, but he'd like to have way more tooling set for JavaScript, because again, there are implementations in various engines, and he'd like to get semantics even out of the implementations. That's even other direction, right? So what I'm getting these days is that I'm pretty sure that in this line, the front end can be used, meaning that the DSL is actually inference rules, right? So premises and conclusion, and premises like left-hand side, right-hand side with some side conditions. That's it. That's our DSL. So it's very general. So we can generate Greek letters, operation semantics out of that easily. And we can generate that term rewriting semantics easily, I think. But the difficult bit is from declarative semantics to algorithmic semantics. In the declarative semantics, everything is just declarative, meaning that we do not need to think about ordering or anything. But if we want to make an interpreter, we need to change that to algorithmic, meaning that do this first, and then this, and then this. Meaning we need to identify binding places, and we need to identify equality checking, all those details. And that's different from different languages. And P4, it's like communicating with all the external peripherals, and we need to either model that or we need a way to sanitize it. So there are many challenges out there. Let's take it for, but I think that this idea it remains the same, but we need more domain-specific information and knowledge about specific programming languages. Thank you.
Yes.
Okay. So first, I was a developer in Mozilla. So I am very happy you put the spider monkey. although you mentioned in the first slide that VA and other VNs are implement the modern features. So spider monkey may be kind of out there. I'm not sure. This is my first question. So whether there's any difficulty when you try to analyze spider monkey? Yeah. So
it's not like there's a difficulty in analyzing SpiderMonkey. It's more like SpiderMonkey's JavaScript engine. Yeah, it didn't cover new features of JavaScript. That's why, because we had to see whether these engines are handling them correctly, but it didn't handle them.
okay. So the second question, because I was working for the JIT part, so whether there's any spec or is it necessary to have a spec for JIT, the behavior of JIT?
So debugging JIT is really difficult, as you know, and there are several papers, more not really in the PL community, but more in SE community or security community. And they do have specific techniques to tackle specific vulnerabilities, but there are several faculty, researchers who want to use our tool to do that, but we haven't done that yet because there are so many bugs to find even before going there.
Okay, thank you.
Thanks.
Has anyone ever approached you about another language with a big spec problem being LLVM?
Not yet. LLVM is not really a high-level language. It's
No, but you're doing WASM, right?
That's true.
They are different, but
That's true, right? WASM is a compilation target in that sense. LLVM could be, but that's too big. Yeah. I forgot to mention this. So Yeah, thank you for the question, because now we are getting invitations from many area and domain specific languages. And what we ask in the beginning is their commitment, right? So it took 10 years for us to work on JavaScript. And after 10 years, we knew JavaScript by heart. So we didn't need any experts. But with WASM, it was possible in 2 years because of Andreas Rosberg and the others. And P4, it's possible because of Nate Foster. And Rust, we have many local experts as well, so I'm not that worried about it. And Ralph Young was like, you know what, your paper was the main reason that I attended PLDI. So Rust people are also interested in our approach. But again, we need their commitment, or we need some idea about the interest of the community. So JavaScript took it, WASM took it. P4, it's that P4 workshop, we gave the presentation to meet the actual people in the community. And they were happy, and they were like, oh, the presentation was so good, and they are willing to take my student as an intern to go proceed. So it's like that, but we cannot tackle everything. So we need anyone who's willing to use our technique with some commitment, then we are happy to work together.
That's a great answer. Thank you.
Thanks.
A good time to. If there is a small. Okay, let's stop.
Yeah.
Thank you very much.
Thank you. Thanks a lot.